Hello guys, you are welcome to this session. In today's class we are going to see how to generate slope deflection equation using double integration method. Okay, I have a sample question for you, and this question comprises a lot of things. Let me quickly read out the question for you. The question says, write out slope and deflection equations for a simply supported beam carrying a uniformly distributed load as shown below. That's A. If the beam is 150 millimeter wide and 250 millimeter deep, has a span of 6 meter and carries a load of 5 kilonewton, determine the maximum deflection at the center, taking it to be equal to 15 giganewton per meter square. Then C part is determine the value of the deflection at 2 meters from support A. Well, as I said earlier, we are going to use double integration method for this solution. And you know, if you have this type of problem and you want to use double integration method, there are two most important things to note. The first thing to do is to always get your bending equation right. So if you have your bending equation, then you can proceed with your integration, first integration and second integration. Okay, so let's go to the solution. So as I said, we are using double integration method, and in this method, in the question, we have a simply supported beam carrying a UDL of W kilonewton per meter run, okay, and a length of L. That's the span length. Okay, so once we have this, because you know the system is already symmetrical, so you can easily get the values of your action, right? Since it is symmetrical system, you don't need to do any calculation. So just know that divide the total load into 2. That's the equivalent point load, because it is a distributed system. It is a distributed load, so you have to convert it to equivalent point load. After conversion, then divide it into 2, so that RA, that is support at A, we carry half of the load, the equivalent point load, and support at B, you carry the remaining half. So in this case, we have RA to be equal to RB, which is equal to WL over 2. You know, WL is like we are trying to convert the distributed load, which is W, by multiplying it by the span, that's the length L. So if you multiply W kilonewton per meter, you multiply it with L, so you are going to have what? The meter in L cancel the other meter, so you have your you have your load in kilonewton, right? That's that. So we have our moment equation here, the bending moment at distance x from A. So what you are going to do is to cut a section. You're going to cut a section. You cut a section and name it x, right? So this is our section x. If this is so assuming this is the beam, assuming this is the beam, okay, so if this is the beam and this side, let's say, is A, this side is A and this side is V. Okay, so we know that the whole length is L, so we are going to call this side X. That's the function we cut. Okay, and if you can remember in our strength of materials course, what we adopted as our sign convention is when you are starting from left, so when you are coming from left, then clockwise moment are positive. That's from left. From right, clockwise moment are negative. Okay, so if you look at this, we are starting from left. Okay, from left, that is from support A. So if I am to take moment here, definitely it is going to be a clockwise moment, because this thing is likely to push this one to rotate in a clockwise direction. So if that is the case, it means our RA is what? Our RA is our reaction at A multiplied by the distance x will give us what? A positive moment. Okay, So which means we have RA times X, and RA is what? RA is WL over 2. So if RA is WL over 2 and we substitute RA in the moment formula, we have WL over 2 times X. That's this portion, okay? That's this part. So we have WLX over 2. Then the second part is this force now, because we have two forces now, so definitely we must have another moment, okay? You know, bending moment, you know, you are not taking moment for the whole span, right? You are just taking moment at a section, okay? So moment at our section X is going to be WLX over 2 minus this second part, the load, the UDL here, the UDL here, okay? This UDL here. So this UDL is W already, we know it's W. So what is the distance? The distance is X. So converting it to equivalent point load, we are going to have what? WX. And the distance from here to X, where we are taking our moment, is half of X, right? So we have WX times X over 2, which give us what? WX square over 2. So the moment equation is going to be what? Mx is equal to WLX over 2 minus WX square over 2. And why we are having negative here is due to our sign convention, as I said earlier, because this one is going to be anticlockwise moment. So if clockwise moment is positive, definitely anticlockwise moment is going to be negative, okay? So this is the first thing to do. After getting your moment equation right, the bending moment equation right, then you move to here and substitute it in the slope deflection, in the deflection, in the integration equation, right? You're going to substitute it here in this EI, the square y, the x square is equal to mx. So the next thing is to remove mx, that's the moment at x, bending moment at x, and substitute it with what we have here, which is WLX over 2 minus WX square over 2. Okay, so this is what I did here. I substituted it here. We have EI, the square y, the x square is equal to WLX over 2 minus WX square over 2. Okay, and the next thing is to start integrating. You know, we said integration is like opposite of differentiation. Differentiation, you are reducing, while integrating, you are increasing, okay? So if you have WLX and you are differentiating, you are integrating, I mean, with respect to x, it means you are going to be adding like 1 to the power of x and then dividing the x with 1 plus the power, okay? As we mentioned, we said integration is something like this. If you are integrating this one, okay, you say you are going to do what? You say x n plus 1 all over what? All over n plus 1, okay? And we are integrating with respect to x because we have the x square here. This denominator is telling us that we are dealing with x, okay? We are integrating with respect to x. So definitely wherever we see x, it is going to be affected by our integration, and if we don't see x, we have to introduce it. Okay, so we have WLX over 2 minus W integral of WX square over 2. So after integrating this, WL is constant. Integrating x power 1, I have x power 2. That's 1 plus 1 will give me 2. And I have 2 here already, which is constant. So 2 times 2, I have 4. Okay. Then the next one, WX square over 2. W and 2 are constant. X square, after adding 1, I have x power 3. Then this 3 times the 2 here, the original 2 here, I have 6. Then plus constant of integration C1. I believe I told you the essence of writing this constant of integration. It is believed that because this is a differential equation, it is believed that it is possible that there may be a constant here at this particular point, C1. Okay, but we don't know, because you know, if you do differentiation, if there is constant, the constant will turn to 0, right? So we are not sure whether there is a constant or not, so we have to indicate, so that after finding it, we will see whether it is there or not. Okay, so let's do the second integration again before we do any substitution. So we are integrating this equation 1 now. which is WLX square over 4 minus WX cube over 6 plus C1. Okay, after integrating, please pay attention to what is happening here. When you integrate the square y dx square, you're going to have dy dx. When you integrate dy dx, you're going to have y. EI is constant. Okay, so we have y to be equal to WLX power 3 all over 12 minus WX power 4 over 24 plus C1x plus C2. You know, I said if we don't have x, we have to introduce x, right? So this C1 doesn't have any x, it is constant. But we know that any number power 0 is 1. So the assumption here is already we have 1 here, and x power 0 is 1, the same thing as 1. If we are to substitute this 1 here attached to this C1, not this subscript C1, no, I mean C1 times 1. So if we are to substitute that one with x power 0, definitely we are going to have x power 1 all over 1, and we know we don't need to raise the over 1. Okay, so that's that. Then plus C2, that's the second constant of integration, so let's move to the next slide. So from here we can start using our boundary conditions. You know the boundary conditions. If you have a simply supported beam, at the support, definitely deflection is 0, but slope is there. At the center, deflection is 0, is maximum, and while that's at the midspan, deflection is maximum, while at the support, while slope is 0. Okay, we don't have slope there. So we know that we are going to use this condition because the first equation, that's the one with EI dy dx is for slope. Okay, so since we are going to start with slope, so we said that at midspan, that is at x is equal to L over 2, half of the span, slope is 0. At the midspan for a simply supported beam, slope is 0. Okay, so if slope is 0, we are going to substitute L over 2 for x and 0 for dy dx in equation 1. After substituting it here, look at what we have. We have 0 to be equal to, because EI times 0 is 0, WL over 4, close open bracket. This is where we have x here before. Okay, so we are substituting for x. So x is now L over 2. We have L over 2, then square it. Okay, we have L over 2, then minus W6x, W over 6x. So here is x also, x power 3. So we remove the x and substituted it with L over 2 power 3, then plus C1. Okay, plus C1. You know, if we don't have C2 in this equation, right? So I can go back to the previous page, but I believe you can remember the equation says we have C1 without C2 there. Okay, so that's the first equation. So after substituting everything, I have WL cube over 16 minus WL cube over 48. Okay, so we are going to take LCM here. I know you have problem with taking LCM. Well, anyway, the LCM is going to be 48 in this case, because 16 can divide 48 into 3. Okay, so we have 48 as our LCM. 16 can go there, 3, then 3 minus 1, I have 2 over 48. 2 into 48 is 2 into 2 is 1, 2 into 48 is 24. That is why we have WL cube over 24 plus C1. So if you take this one to cross the other side of the equation, you're going to have minus WL cube over 24. Okay, so I believe you can practice this one. This is what do you call it, elementary arithmetics. The next one is the to substitute this C1 in the equation 1. After substituting C1 in the equation 1, we have equation 3. Okay, this is the equation. We have substituted C1 here, C over C1. Okay, so now we have equation 3, EI dy dx is equal to WLX square over 4 minus WX cube over 6 minus WL cube over 24. Okay, so let's move to the next slide. So at support A, that is when x is 0. So this part now, to find C2, you can use either of the support, either support A or support B. Okay, we know that at support A, x is 0 because we started from left. Okay, So if you are going to use support B, x will be L. Okay, and as I mentioned earlier, definitely deflection is 0 at this particular point. So at support deflection is 0. So at x is equal to 0, y is equal to 0. So we are going to substitute this into our equation 2. The equation 2 is the one with C2. So after substituting everything, the values will be 0. Okay, everything will be 0 because we have x attached to all the parameters. We have x attached to all the parameters. So definitely we are going to have everything return to 0. And if everything is 0, then definitely C2 will be 0. Okay, so we have C2 is 0. So we are going to substitute the value of C2, which is 0 here. We have substituted it. So in that is we are substituting in that equation 2. I can't go back to the previous slide. That is why I am not showing you the previous equation. Okay, so we have WLX cubed over 12 minus WX power 4 over 24 minus WLX L cubed over times x all over 24. This is our equation 4. Okay, so the next thing is to find the deflection at the midspan. We find the deflection at the midspan. Okay, so we can also find the maximum slope if we like, but let's just find the maximum deflection at the midspan. I'm supposed to include this in the question, maybe I forgot to add it. We are finding the deflection at the midspan. That's the y max is at when x is equal to L over 2. So we are going to use the last equation we have, that's equation 4, because that is the one with EI y, and we have already found our C1 and C2. Okay, so we are substituting L over 2 into this equation. We have x power 3 here, we have we have x power 4 here, and we have x here. So removing x here and here, we are removing x here and here and here, and substituting the x with L over 2. So after doing the substitution, we have L power 3 times L, which is L power 4. We have L power 4 here, we have L, I think here is an error. We're supposed to have L cube, not just L. So we have L cube here. L cube times L will give us L power 4. Okay, so 2 power 3, which is 8 times 12 will give us 96. Okay, because because it is bracket, you have to power everything. 2 power 4, 2 power 4 should be, that is 8 times 2, right, which is 16. 16 times 24 is 384. Then here is just 12 times 2, which is what, okay, I believe this is a typing error, because this one is the value of our what, C1, and C1 is WL cube over what, over 24. So definitely this is a typing error, sorry about that. It is 24. So 24 times 2 will give us what, 48. That is how we have this 48. Okay, so I can't go back to the previous slide. That is why I will not be able to show you. So after taking LCM here, the LCM happens to be 384. So if you take LCM here using 384 as your LCM, 96 into this, 48 into this, at the end of everything you are going to have 5 WL for 4 all over 384. Okay, so you are going to have this, and it is negative. It's going to be what? It's going to be negative. Okay, and the negative is nothing, it is just telling you that deflection is downward. Okay, it's downward. So this is the final equation. You divide both sides by EI so that you remove the EI from Y max. So we have Y max to be equal to minus 5 WL for 4 all over 3H4 EI. Okay, so this is our maximum deflection equation. As I said, you can establish for slope if you like, but it is not part of this slide. So let's move to the B. The B said we should find the maximum deflection, and we were given some values. That is the depth and the width of the beam is given as 150 and 250. Okay, width of 150 and depth of 250 millimeters. So you have to crack your brain, because if I is not given, definitely there is no way you're going to solve it without using I. So your answer must be in terms of I. That is why the B and D is given, and we know that I is moment of inertia, and the formula for moment of inertia or second moment of area is B d cube over 12. Okay, so before you substitute anything, please make sure that you convert this to meters, because all our other parameters are in meters. So converting this to meters is far more easier than converting the others to millimeter. So after converting 150 millimeter to meters, we have 0.15. After converting 250 millimeters to meters, we have 0.25 meters. Okay, so BD cube over 12 give us what? 1.95 times 10 to the power minus 4 meter over 4. Okay, so we are going to use the maximum dy max to get the maximum slope, maximum deflection. So y max is equal to what? WL for 4 all over 3 at 4 EI. All over 3 at 4 EI, which is equal to what? We know that 5 is given in the question as this 5 is there already. Then 5 is given as the load 5 kilonewton 5 meter. Then L is given as 6 meters. So substitute everything. This one is given as 15 giganewton per meter square, 15 giganewton per meter square. So what I did here is I tried to, because we have this 5 in kilonewton, so instead of using giga, which is 10 power 9, I converted it. I removed 3 powers from it and give it to kilo. Okay, so that I will have 10 power 6 kilonewton instead of 10 power 9 newton. Okay, so I have 10 power 6 kilonewton. That's the giganewton per meter square. Then we have 1.95 times 10 to the power minus 4 meter per 4. So after functioning calculator and substituting, solving everything, I have 0.0288 meters, which is equivalent to 28.8 millimeters. So this is to tell us we have 28.8 millimeters deflection based on the data we use. Okay, and that's about 2.8 centimeters. So this is that. So let's move to the C part of the question. The C part asks us to determine the deflection at 2 meters from support A. We know support A is at the left, right? So which means 2 meters at x is equal to 2, because we started our section, we got our section from what? From A. From A, we have our x from A. So definitely it means at x is equal to 2. Okay, it says 2 meters from support B, then we have to do 6 minus 4. 6 minus 2, so that we can get our x from A. Okay, so here we are not going to use the maximum slope deflection. We are going to use the equation 4. That's before substituting L over 2 to get the y max. Okay, so this is the equation W. So this is the equation WL x cube over 12 minus WX over 4 all over 24 minus WL cube x over 24. So if you go back to the video, you see the actual equation. So we have what? We have the equation now. So all we are going to do is to substitute the parameters, substitute the values. For W we know is 5, L is 6, and X is given as 2. So substitute it here. Then here also we have 5, 2, 4, and 24. Then here also we have 5 times 6 for 3 times 2 all over 24. So if you solve this part, you're going to get what? That's 20. Because 6 here is 1, 6 here is 2. Then 5 times 8, 40, you have your 20. Here is I think 3.33. Then here is 90. So 20 minus 3.333 minus 90. So if you substitute all the values and punch your calculators, if you don't know how to use calculator, please ask your colleagues to show you how to use calculator. Because if you have denominators and you want to do it all at once, definitely you must use bracket. You must learn how to use bracket in solving these fractions. Okay, at the end I got 0.025 meters, which is equivalent to 25 millimeters. So at this midspan we have 28.8 millimeters. That's where we have the maximum. Then at 2 meters from support A we have 25 millimeters. So I think this is the end of this thing. So this is the end of the 3 questions asked. That's the A, B, and C. And if you have any question, please feel free to ask me or ask your colleagues for a clarification. This is going to serve as our revision class for this particular topic, because this question covers everything. So if you are using cantilever or whatever, whether with UDL or with point load at the end or with point load at any point, so you're going to apply the same principle.